recording. Every Tuesday, Thursday, I gotta get my daughter to school at McKernan, Belgravia. I'm in Mill Woods, so I gotta drive to Southgate Mall, drop her off, and then come back in time for this. 8 o'clock was never gonna work. I was like 8:30, just barely makes it, but good. So let's recall what we were doing last time. No questions in the chat. Okay, good. So recall, we're doing hyperbolic functions and their inverses. So the three main categories of transcendental functions we have are trigonometric functions, which will focus on sine and cosine and tangent. Then we have, and their inverses, arc sine, arc cos, and arc tangent. And then we have exponential functions and their inverses, logarithms, in particular e to the x and natural log x. And then we have hyperbolic functions, which are the third category of transcendental functions and their inverses. And we'll also focus on sine hyperbolic, cos hyperbolic, tan hyperbolic, and their inverses, arc sine hyperbolic, arc cos hyperbolic, and arc tan hyperbolic. So when we're doing this, what we have is the first one is sine hyperbolic is a function which luckily goes from R into R. So that means that inverses, remember now, this is no new story for inverse type scenario. It's always the same. That means that the inverse is going to be sine hyperbolic inverse is going to also go from R to R. And we can obtain the graph by reflecting about the line y equals x. In this case, sine hyperbolic looks roughly like x cubed. And therefore, what that means for us is sine hyperbolic inverse looks roughly like the inverse of x cubed, which is x to the 1/3. So this will be sine hyperbolic inverse. If we look at, I'm just going to run down through the three guys, and then we have explicit formulas using natural logarithms for these, for the derivatives, etc. Remember, every time we get these functions, I get sine and cosine and tangent. I want to now know what the derivatives of those guys are, what the integrals of those guys are. And then I got the inverses of the trigonometric functions. I want to know what the derivative of the trig functions are and what the integrals of the trig functions are. Then we get the exponential functions. I want their derivatives and integrals. Then I get the inverses, logarithms. I want to know their derivatives and integrals. Now we have the hyperbolic functions. These are their inverses. And then I'm immediately going to do their derivatives and their integrals. And this is when we can segue into, well, we'll do L'Hopital's rule. But after we do L'Hopital's rule and a bit of this, we will do integration. So 2 is cosine hyperbolic. Cosine hyperbolic is a function which is going from where? It's going from, technically speaking, R into I'll do it this way. You'll see it in the video then, at least. R into where? 1 infinity, but this is not 1 to 1. Therefore, we're restricting to 0 infinity. Then cos hyperbolic x is 1 to 1. And we get cos hyperbolic from 0 infinity into 1 infinity. That means that we're going to get the inverse cos hyperbolic inverse is going to go from 1 infinity to 0 infinity. What that means pictorially for us is, again, cos looks like x squared shifted up 1, but it's only 1 to 1 here. So this is cos hyperbolic. And then its inverse will go from 1 to infinity, the domain. And then so its range will go. So it looks like x squared and its inverse root x, but this is cos hyperbolic inverse of x. And then 3 tan hyperbolic x is the function we saw with the limits last time, that it has a horizontal asymptote of 1 in the positive direction and -1 in the negative direction. So tan is going from r into -1, 1 open. We can't actually touch them. Those are horizontal asymptotes. It's a bounded function. That means that tan hyperbolic inverse is going from -1 to 1 into r. What do we get from this pictorially? Our pictures look like, the more you can see the graph immediately, the better you can do these weird limits of transcendental functions. Just like when I want to know limit as x approaches infinity of x squared or something like this, I know it's infinity because I can picture what x squared looks like. So the more that you can picture these, we're about to do L'Hopital's rule and weird limits, but when you can picture some of the limits, you're not going to be able to picture these functions anymore. But when you can describe the behavior of some of these functions near values or at infinity, it will make it a whole lot easier to do L'Hopital's rule and decide whether I have infinity over infinity or 0 over 0 type of these new transcendental functions. So what do I get? I get that tan hyperbolic was going from 1 to -1. And so its inverse is going from -1 to 1. I lost my axis now. And then we're going unbounded. So those are the 3 main ones. You can look in books if you want for the others, for secant hyperbolic inverse and cosecant hyperbolic inverse and cotan hyperbolic inverse, but you find their inverses the same way. You restrict to a domain if not 1 to 1 if necessary, and then you interchange the domains and you get the graph by reflecting about the line y equals x. When we do this, and remember the cancellation, f following f inverse of x is f of f inverse of x, which just should equal x, and f inverse following f of x should equal f inverse of f of x, and that should just equal x identity. F following its inverse, or the inverse following the function, should leave you at the same point. And then so we have these for all of the transcendental ones. Sine hyperbolic of sine hyperbolic inverse of x equals x for x in R. Remember, this is for in the domain specifically. For this first one, this should be y technically. Make yourself remember how this goes at first. Oh, gray. Gray. So f is going from A to B, means that f inverse goes from B to A. And so if you're doing f inverse first, then you have to go from B, and this would be for x in A. Sine hyperbolic is nice because it's the only one that goes from R to R, so there is no restriction in the domain. So then this means that sine hyperbolic inverse of sine hyperbolic x is also equal to x for x in R. Let me do and this should be y technically. But you have to restrict this for the domains. Cos is going to be from where cos is going from 1 infinity. So if we do cos hyperbolic of cos hyperbolic inverse of y, it should equal y for y inside 1 infinity. And then cos hyperbolic inverse of cos of x should equal x for x in its hyperbolic domain where it's 1 to 1, which is 0 to infinity. So what that's saying is cos hyperbolic inverse of cos hyperbolic of -1 does not equal -1 because -1 is not inside 0 infinity. Cos hyperbolic is even though, so cos hyperbolic of -1 is equal to cos hyperbolic of 1, which is equal to whatever this value is going to be. But you can't just cancel them off. You can only cancel when you're in these domains. All right. Now we have specifically, we're going to have, theorem next. I'll just show one. I don't know if you have to do one for your homework or not, but I will post this shortly. Because we can algebraically solve now, before we had that e to the x is a 1-to-1 function, it definitely passes the horizontal line test. But the problem is we have no algebraic way to solve for what the inverse is. So John Napier gives it this term, a logarithm. And this is the logarithm is the inverse of exponential. But because now it's specifically because of e to the x, and we know how to take the derivative nicely, and e and log cancel each other, we can cleverly use this to solve for the inverses of the hyperbolic functions for an algebraic expression involving natural logarithms. Because sine hyperbolic, cos hyperbolic are linear combinations of e's, essentially. If there's any justice in the world, the inverse should involve natural logarithm, which it does. So theorem, the inverse hyperbolic functions are expressed explicitly using logarithms. So 1, sine hyperbolic inverse of x is equal to the natural log of x plus the square root of x squared plus 1 for all x in R, because that's the domain of sine hyperbolic x. 2, cos hyperbolic inverse of x is equal to the natural log of x plus the square root of x squared minus 1. And that's for x, of course, in the domain 1 infinity. And then 3, tan hyperbolic inverse is equal to 1/2 the natural log of 1 plus x over 1 minus x for x inside -1, 1. If you want to take 214, the next calculus class, we do power series representation, and we want to know what the power series representation of natural log x is, or 1 minus x. We can get this nice power series, and then because of this formula is extremely important for finding the power series representation of tan hyperbolic inverse. If you want to see this, you'll have to take 214. So I'll prove part 1 for the sine hyperbolic inverse. What are we saying? So first of all, what we use is we use the definition of inverse. So we know that y is equal to sine hyperbolic inverse, and that's if and only if by definition sine hyperbolic y equals x. But if we want the derivative of that cleverly, then we would take the implicit differentiation now. But what we can also do is we can use the definition of what sine hyperbolic is and solve for y. So this is by the definition of sine hyperbolic. This says that x, oh, I hit gray again. Sine, so that x is equal to e to the y minus e to the negative y over 2. This is just our definition. And that, of course, we can write as 2x equals e to the y minus e to the negative y. What I now want to do is I want to solve for a quadratic in e to the y. So if I bring this all to one side, we're going to get e to the y minus e to the negative y minus 2x equals 0. If I multiply by e to the y, we're going to get e to the 2y, or e to the y squared, and you can see it, minus 2x times e to the y minus 1 equals 0. So I have a quadratic in e to the y. I let z, I use a new variable temporarily to simplify this. This is a clever trick just to show you how to solve equations for other variables in general. And then we'll resubstitute what it is after. So this tells us that z squared minus 2xz minus 1 equals 0. So what do I want to do with this? I want to complete the square. So b is negative 2x, b over 2 is equal to negative x, b over 2 squared is equal to negative x squared, which is x squared. So this is z squared minus 2xz plus x squared minus x squared minus 1 equals 0. This is now a perfect completed square in z. This gives me what? Once I complete the square, this gives me z minus x squared equals x squared plus 1. This tells me that now I'm solving for z. Z minus x is equal to plus or minus the square root of x squared plus 1. And we know that e to the y, which is equal to z, is greater than 0. So we choose the positive square root. This says that z minus x is equal to positive the square root of x squared plus 1. Or z equals x plus the square root of x squared plus 1. But z equals e to the y equals x plus root x squared plus 1. We were solving for y originally, so natural log both sides. And we get y is equal to the natural log of x plus square root of x squared plus 1. But y equals sine hyperbolic inverse of x implies that sine hyperbolic inverse of x is equal to the natural log of x plus the square root of x squared plus 1. So this is how you can do this for cosine and cosine hyperbolic and tan hyperbolic. Well, and now we want the derivatives of them. I can just basically use so now the strategy is I can use either these formulas or use the definition and find the derivative this way. Just using the clever trick and using, so when we did this for trigonometric functions, what I did is I said y equal to sine inverse x. Therefore, x equals sine inverse or sine of y. I implicitly differentiate. I have the formula for the derivative of y already. We take these clever formulas and then we use a right triangle to get back, and trigonometric identities essentially to get back to what the expression for the derivative of arcsine is. We can do the same thing for the hyperbolic functions, or now that we have this theorem, I can just take the derivatives because we already know what the derivative of log is, 1 over itself, and then I can use a chain rule, take the derivative of the inside. So that's essentially what we're going to do now, is the derivative of these guys. The derivative of hyperbolic and inverse hyperbolic. So the derivative of the hyperbolic functions, I'll list all 6 for completeness, but again, we're going to focus on sine hyperbolic, cos hyperbolic, tan hyperbolic when we do exams, etc. Assignment, you can look the formula up so that they may still appear on assignments. But what I want to do is, these are the easiest ones to take derivative. If you can't remember, y is sine hyperbolic x, for instance, is just e to the x minus e to the negative x over 2. So if you really want, the derivative is going of sine hyperbolic x is nothing other than the derivative. If you get stuck and can't remember, the hyperbolic ones are the easiest ones to derive themselves. Just use the definition, and e is its own derivative. This is e to the x minus e to the negative x over 2. It doesn't even care about the 1/2. And I can split that as a sum. So what is this? It's supposed to be a 1/2. That's going to be equal to 1/2 e to the x, and then minus negative e to the negative x by the chain rule. So that's 1/2 e to the x plus e to the negative x, which is, of course, by definition, cos hyperbolic x. So what that says is the derivative with respect to x of sine hyperbolic x is equal to cos hyperbolic x. The derivative of its inverse, again, you can just use the definitions, but the derivative of cosecant hyperbolic x is going to equal negative cosecant hyperbolic x cotan hyperbolic x. The derivative of cos hyperbolic x is just equal to sine hyperbolic. There's no negative in this. The derivative of its inverse is negative secant hyperbolic x tan hyperbolic x. Remember, those are just clever ways of writing out the definitions of everything and taking the actual derivatives. And then the derivative of tan hyperbolic x is secant squared hyperbolic x. And then its inverse, the derivative of cotan hyperbolic x is equal to negative cotan hyperbolic, or cosecant. So the way I remember it is, if you're just going to memorize everything, the derivative of sine is cos. There's no negatives on the 3 that I make you memorize. essentially. And then the other ones, there's a negative on each of the inverse ones. So now it's derivative of sine hyperbolic is cos hyperbolic. Derivative of cos hyperbolic is just sine hyperbolic. There's no negative. And the derivative of tan hyperbolic is secant hyperbolic. The derivatives of the other ones are basically the same formula as 2, but there's a negative on everybody. Negative, negative, negative. So those are derivatives of the hyperbolic functions. Now I want the derivatives of the inverses. For the derivatives of the inverses, what we can do is I know. I'll tell them you're loud outside. What do you want? He's going. I don't know if you can hear him in the background, but he's meowing. Being a bad cat. What do you want? You just want to hang out? We can use the formula. Sine hyperbolic inverse is equal to. You can't even see him unless his eyes turn on. This is the natural log of x squared plus, or sorry, x plus the square root of x squared plus 1. So how am I going to take the derivative? The derivative of sine hyperbolic inverse of x is going to equal the derivative with respect to x of the natural log of x. Okay, where are you going? Okay. X plus the square root of x squared plus 1. That by definition is equal to 1 over x plus the square root of x squared plus 1. You're not helping, Kitty. You're not helping. Times the chain rule. I have to take the derivative of this thing. So that's going to be equal to 1 plus 1 over 2 the square root of x squared plus 1 times x. Sorry. By the chain rule, and then that will cancel. So what I'm doing is essentially I'm taking, why are you up here now? His butt's in the way, Kitty. Now I'm just going to simplify the derivative. This is equal to, what are we going to get? I'm going to count a common denominator. So this is x plus the square root of x squared plus 1 times now I have the square root of x squared plus 1 plus x over the square root of x squared plus 1. These two things cancel each other now, if you see. And we get just 1 over the square root of x squared plus 1. So what does that say? That says that the derivative with respect to x of sine hyperbolic inverse of x is equal to 1 over the square root of x squared plus 1. The three that I'm going to make you memorize are the derivative and now of cos hyperbolic inverse of x is going to be equal to just 1 over the square root of x squared minus 1. If you do the same trick and write out what the definition. Yeah, they wait till I'm doing math and then they're like, oh, what are you doing? I'm jealous. And then they get in the way. That's what he waited for. He was ignoring me. I even have the front door open because it's nice and it's reasonable out. So I opened it right before I started. And then he just comes in and messes with stuff because it wouldn't be fun to interrupt if I wasn't doing math first. And the derivative of tan hyperbolic inverse of x is going to equal 1 over 1 minus x squared. And then the other three, I guess I can, but these are the three I'm going to make you memorize for exams and formulas, etc. And then the other three are the derivative with respect to x of cosecant hyperbolic inverse of x is equal to -1 over the absolute value of x, the square root of 1 plus x squared. The absolute value comes in play when we have to look at the domains of the inverses, remember? And then the derivative of, I'll keep this, secant hyperbolic inverse is going to equal -1 over x times the square root of x squared minus 1. You don't need an absolute value here because on secant, because cos hyperbolic is positive anyways. And then the derivative of cotan hyperbolic inverse is equal to, so those are the other three that you don't really have to memorize. The first exam, when is this? It's not next week, or is it next week already? I'll send this out, but it's going to be online, I guess, because they don't want us going in class until February or something, and they keep changing it. So yeah, Thursday, February 3rd, that's what I thought. That's the day before my birthday. My birthday's on a Friday finally. So yeah, we're gonna do it in class through or online through CrowdMark. I'll send out an email about this as well. Thanks for reminding me. Yeah. I knew we still had time, but because the way everything's going, yeah, I'll narrow down and give you some practice questions as well. Probably tomorrow sometime. I'm not the only section of 115 this semester. There's other sections, so I'm not the coordinator. So I have to wait till they send exactly what they want and what the cutoff is, etc. So it'll be closed. But yes, I'll give you some questions that will narrow down. But basically, probably everything up to this week would be fair game. But this is the derivative now. So now we have the hyperbolic functions and their derivatives, and the inverse hyperbolic functions and their derivatives. So for us, we have now 12 more formulas, regularly 24, because we have the 3 trig functions, or the 3 hyperbolic functions and their derivatives, and then the 3 inverse functions and their derivatives. So that gives us 12 more functions essentially that we have to worry about. What else did they say I had to do today? Yeah, okay. See. Yeah. I was gonna segue, but usually I would leave this. I was just musing to myself. We're gonna have to do the integrals of all of these functions as well. But we can probably do a few of these because you already know a substitution rule in theory, and then we have to do L'Hopital's rule before we get into it. But we'll do the start of integrals of transcendental. So the first way we get these are for the trigonometric and their inverses. Trigonometric functions, first of all, we know all of their integration by either just using the fact that we know that what the derivative is, or our first game that we play in 114, which is substitution rule. So how do we get these? We know that the derivative with respect to x of sine x is equal to cos x. Therefore, if I integrate both sides, integral and derivative are inverse operators of each other. So when they touch, they cancel it. There's a cancellation law. So the integral following the derivative of sine should just leave us our values that cancels off. So this gives us sine x is equal to the integral of cos x dx, or the most general antiderivative we learned is up to a constant, so plus c. The integral of cos x dx is equal to sine x plus the constant of integration is the most general antiderivative. I see you too. Antiderivative. So because I know the derivative of sine, I know the integral of cos is what we're getting at. The integral of cos x dx is equal to sine x plus c. Similarly, the integral of sine x dx is equal to what? Negative cos x plus c. Because when I take the derivative, I should get the integrand. The derivative of negative cos x plus c is equal to negative sine x plus 0, which is sine x. You should get the integrand. When you take the derivative of the right-hand side, you should get the integrand in the left-hand side. They're inverses of each other. All right. The next ones are, I'll do integral of tan and secant because these are important when we do integration rules. I'll remind you when we get there as well, but it's a substitution rule and a clever trick for tan. The integral of tan x dx is equal to the integral. Whenever you're stuck with trigonometry, the first rule is write out the definitions of what everybody is, turn everything into sine and cosine. So this is sine x over cos x dx. Do I have a function and its derivative? Yes, essentially I do. I'm going to let w equal cos x, then negative dw is equal to sine x dx. That tells me that the integral of sine x dx over cos x is equal to the integral of negative dw over w, which is equal to negative the natural log of the absolute value of w plus c, which is equal to negative the natural log of the absolute value of w was cos x plus c. And then the book puts it as a natural log. The negative on the outside, this becomes a natural log of 1 over cos x plus c. The negative on the outside became the exponent on the inside. And then 1 over cos is secant. So that says, long story short, the integral of tan x dx is the natural log of the absolute value of secant x plus c. And so those are the three that I'll make you memorize, I guess. The other ones are a little trickier. And then so for secant, what the trick for secant is a really dirty trick. So steal it from me now. The integral of secant x dx is equal to, I want to use substitution rule. So I want to multiply by 1 in the form of something over something, where on the bottom I have that once I multiply on the top by this secant guy, I'm going to get exactly its derivative. So the derivative of secant is secant tan, and the derivative of secant tan is secant squared. So what we're going to cleverly do is multiply by secant x plus tan x, but that's crazy. It would change it. So we multiply and divide by secant x plus tan x. Now notice what happened to that. That says that we have the integral of, now let me rearrange it, secant x tan x plus secant squared x times dx on the top, and then on the bottom I have secant x plus tan x. What's the derivative of secant? secant tan. What's the derivative of tan? Secant squared. So now I'm going to let W equal secant x plus tan x. That says dW is immediately equal to secant x tan x plus secant squared x dx, which is exactly what I have. So this integral becomes the integral of 1 over W dW, which is equal to the natural log of the absolute value of W plus C, which is equal to the natural log of the absolute value of secant x plus tan x plus C. This will become extremely important when we do trigonometric integrals later on. So the integral of secant x or secant 1x is equal to the natural log of secant x plus tan x plus C. When we get our first real integration technique in this class, integration by parts, we're going to see that integral of secant cubed, the next odd number, is a reduction formula to knowing how to do this integral essentially. And then secant 5, it reduces secant cubed, then secant 1, and then you play this game all the way down. Turtles all the way down. So similarly, I won't derive them for you. You get the idea. But for cotangent, the integral of cotan x dx, you use substitution rule again, because cotangent is cos over sine. You're going to get the natural log of the absolute value of sine x plus c. And the integral of cosecant x dx is equal to the natural log of cosecant x minus cotan x plus c. We know the integral for free. I already showed it once, but I can do it again for the exponential functions. We're going to get, we know that the derivative with respect to x of a to the x is a to the x ln a, and ln a is just a number which is not equal to 0. And as a is 1, but we're assuming a is strictly larger than 1. If a is 1, it's just 1 to the x is just the constant function 1. The derivative is 0. But now what I can do is integrate both sides. And those will cancel. This says a to the x is equal to the integral of a to the x ln a dx, which is ln a integral of a to the x dx, because ln a is just a number. So I'm solving for, I want the integral of a to the x. This says that the integral of a to the x dx is equal to a to the x over ln a, plus of course a constant of integration is the most general antiderivative. So this is the integral of all exponential functions, in particular. The integral of e to the x is e to the x plus c, because e is its own derivative. Oh yeah, I can't really do that one yet. I can do that one. Here's where we're going to start getting into where I have to segue and say we have to let this go. And when we get integration techniques, we will do most of the rest of them. And we have to do L'Hopital's rule and some curve sketching stuff this week before we start integration full on next week and do our exam, etc. So following what the coordinator wants as the curriculum, the last guys we have are integrals of the hyperbolic functions. And then we'll start their inverses. So again, because the derivative with respect to x of sine hyperbolic x is cos hyperbolic x, we can integrate both sides. We can cancel, and we see that immediately the integral of cos hyperbolic x dx is equal to sine hyperbolic x plus c, and the integral of sine hyperbolic x dx is equal to cos hyperbolic x dx plus c. So we get, by knowing the derivative of sine hyperbolic and cos hyperbolic, we know the integrals of sine hyperbolic and cos hyperbolic as well, because they turn into each other. For tan hyperbolic, we can use substitution rule again. This is the integral of sine hyperbolic x over cos hyperbolic x dx. So I'm going to let w equal cos hyperbolic x. So dw is equal to sine hyperbolic x dx. And this becomes the integral of 1 over w dw, which is the natural log of the absolute value of w plus c, which is the natural log of the absolute value of cos hyperbolic x plus c. You can take off the cos hyperbolic. You can write this as, so the integral, the moral of the story is cos hyperbolic is always positive. So you can take the absolute values off if you want. If you're scared, leave them on there. But the integral of tan hyperbolic x dx is equal to the natural log of cos hyperbolic x plus c. We can get at the other ones. I need partial fraction decomposition, essentially. But the integral of secant hyperbolic x is equal to, I'll start this off, and then I'll show you this is the integral of 2 over e to the x plus e to the negative x dx. What I really want to do is cleverly multiply by e to the x over e to the x to cancel the negative one. This gives me 2 times the integral of e to the x dx over e to the x squared plus 1. So then I'm going to let w equal e to the x. So dw is equal to e to the x dx, and this equals to the integral of 1 over w squared plus 1 dw. For cosecant, I need partial fraction decomposition, but this one I can sneak in there. This is equal to what? 2 arctan of w plus c, which is equal to 2 arctan of e to the x plus c. So this starts becoming a weird formula. But what that says is the integral of secant hyperbolic x dx is equal to 2 arctan e to the x plus c. And then I have to use partial fractions for the cosecant hyperbolic. I'll try to remind myself, or you can try to remind me in a couple of weeks when we get to partial fraction decomposition. I'll show you how to use that in the substitution. The moral is sometimes you need more than one trick to get out of this. First, I had to know what the arctan formula, or first I needed to know a substitution rule, clever business, and then I needed to see the clever trick of arctangent formula, because the derivative of arctan is 1 over w squared plus 1. I know this integral. And then the last two are the integral of cotan hyperbolic x dx is equal to the natural log of the absolute value of sine hyperbolic x plus c. I can use substitution rule again, but for cosecant hyperbolic x, we need to use partial fraction decomposition. When I do that, we get the natural log of e to the x minus 1 over e to the x plus 1 plus c. So those are the integrals of all the transcendental functions, integrals of inverses. I know I'm done, so what are we going to do with these guys? All the inverses are found using one method called integration by parts. Indefinite integrals are found using an integral technique called integration by parts. So we will continue this story after we do L'Hopital's rule. So I'll probably start L'Hopital's rule, or I'll do some examples of derivatives and stuff starting on Thursday morning. But then we'll clean up this. I think they have L'Hopital's rule squeezed in there, limits and taking the derivatives of the ratios of certain kinds of limits in indeterminate forms. And then we'll get to all these integration techniques and applications, which is essentially the rest of the course. So the rest of the course will be, other than L'Hopital's rule and cleaning up how to take limits of these new transcendental functions. The idea is to get all of these new integration techniques. One of the major applications of integration by parts is it allows us to find the integrals of all of the inverse transcendentals. So the integral of arc tan x dx, or the integral of log x, or the integral of secant hyperbolic -1 dx. All of these guys are found using integration by parts. I will see you on Thursday, I guess. I'm over in a couple minutes.